Hi, kiddos. This is lesson 5 of Forces in Motion. Today we're going to be observing the forces of motion. On Google Classroom, I posted this link and it's called It's a Drag. It is one of our interactive simulations so that you can experiment and explore with the idea of different amounts of friction, different amounts of drag, things like that with this. It's pretty neat. I hope you enjoy it. So we're going to start out right now with the book, our Learned Notebook, and we're going to start with Bell Ringer number 9. Oh, and one more thing. Um, in your packet on page 15, after you finish It's a Drag, you do have some questions, and I will be posting those on Google Classroom. So make sure that you're responding on there. All right, so on number 9, how might drag impact motion? Remember that drag is air resistance. So how will that affect motion? Did you say that it will slow it down? There we go, got it to come out that time. Yes, it will slow it down. Remember at any time, if I'm going too fast, pause the video, finish what you're doing, and then press play. On number 10, a man standing on the ground experiences the pull of gravity and the force of the ground pushing him up. The two forces are equal, or did you say balanced? If you didn't, please write balanced in the blank. Make sure that you make corrections. If you made a mistake, you're only human. So correct these mistakes. Don't just mark it wrong. You need this stuff to study later, so make all the corrections and notes that you need. Let's look at bell ringer number 11. Two teams are playing tug of war. Team A loses when Team B pulls them across the center line. What is true about the forces acting on the rope? Did you say they are unbalanced? That would be correct. Number 12. When a bat strikes a ball, what is transferred? Now we're talking about the wooden or metal bat, not this little old flying animal, looks like a chicken nugget with wings. None of that. We're talking about the sport of baseball. So when a bat strikes a ball, what is transferred? Energy is transferred. Number 13. What force occurs as objects slide past one another? So it slides past. Did you say friction? That would be correct. I feel like Dora the Explorer. Number 14. Which is not a unit used for measuring distance? Think back to when we studied the metric system. Remember, King Henry died unusually drinking chocolate milk? So what unit is not used for measuring distance? Remember, let's look at the roots. We have meter, 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 liter. So which one is it? Liter would be correct. Liter measures liquids. So please take that note down. You have meter that measures distance, liters that measure liquid, and grams that measure weight. And then it increases or decreases on the metric system scale of King Henry died unusually drinking chocolate milk, with the U standing for the single unit of 1 liter, 1 meter, or 1 gram. So make sure you know those. It's very important in science to know that. I'm still learning it. I learn something all the time about it. So let's go ahead and turn to number 15. A change in position over time is called motion. A change in position over time is called motion. Did you say motion? Okay, got to get into the Dora Explorer mood. Come on now. Number 16. What may be used to show changes in motion? I bet it's those old bubble maps. I'm not even sure what a bubble map is. It would be a distance time graph, and we're going to be studying those. Those are very important for you to be able to understand. Just because we may not be here and be studying toward an EOG like we normally would be, because these would be on your EOG, you're going to have to face these distance time graphs in 6th and 7th grade. So you're going to need to know them. It is super important. Remember, I don't tell you something is important if it's not. I don't waste your time with that. This stuff is getting you ready for 6th, 7th, and 8th grade. So we've got to know these things. I have a lot of different things I could be doing right now besides this. This is important. Let's go ahead and turn to number 17. And this is what a distance time graph is going to look like, except it's going to be labeled with distance and time on there. And I promise we'll go over that and in the next few days coming up, next week's lessons. So make sure that you are focused and staying on top of this and studying. Which graph represents a decrease in motion? This would be B. As you can see, it had some motion going, and then it starts to taper off and slow down, and then it would be leveling out and just traveling either straight or possibly coming back down. It's easier to tell when the graphs are labeled. Let's look at number 18. It says, which graph represents a steady motion? Steady means that it doesn't change, that it goes on in the same way over time. It doesn't get faster, it doesn't get slower. Now we see that A, we see there's a change. With B, we see there's a change. But with C, it starts out the same and it stays the same through here. And you might be looking at this one and saying, well, why isn't it this one? Well, this would be like time down here at the bottom, and this would be distance here, and this one is staying the same. So it's actually whatever this is. Let's say it's a car. This car would be stopped. It wouldn't be moving. It wouldn't be going anywhere. It had made it so far from its origin. It made it here, and maybe it parked. And so it just stayed put, and its distance wasn't increasing, but its time was. So it was staying parked in a parking spot for an extended period of time, for example. Whereas this one, this is just, it's like kind of like a merry-go-round where it stays the same speed throughout. Now I would like for you to turn to page 14. Inertia, remember, that's the starting and the stopping when you would feel your body moving. This is the tendency of an object to resist the change in its motion. So this is when you have an object, it wants to stay at rest or stay in motion. And Sir Isaac Newton was the first to describe this in his first law.
Let's start with the tablecloth. It looks just like a regular piece of cloth, but it's not. In fact, a real tablecloth looks very different on the edges. Here's a real tablecloth. It has this little hem that's right here. It makes it look nice. They fold it over, and that's horrible for this particular trick because it can catch the edge of something and throw it on the floor. So you don't want that. You want a piece of cloth that you've actually cut. Look at this. There's no hem, so you can see it doesn't look great, but it's perfect. It's going to slide right out from under the dishes, and that will be great. Next thing, you don't want anything on the table that can catch. A nice smooth surface. Friction is our enemy. And as we set the table, we have to be careful of the dishes we select. Look at these. I went to a garage sale and found some dishes that will be perfect. The bottom is what I'm most concerned about. I want to make sure there's nothing that's on the bottom that could actually catch on the tablecloth. This is a nice smooth surface. This should be really good. All right, so if we set the table, maybe a bowl over here like this, that'll be great. Some silverware, good. And I don't know, a glass. That's perfect. All right. The secret is the pull. You see, the inertia that we have here in all of these objects, the tendency of an object to stay at rest until a force acts upon it, I only want the force of gravity really acting upon it to hold it in place. So the action where I'm pulling this out from underneath would normally pull this off the table unless I do it quickly and I use the edge of the table to help me out. Let me show you what I mean. Here on the side like this, I'm going to hold on to the tablecloth kind of like this. See how I'm bunching it up a little bit? I want to get as close to this edge as possible. And the biggest mistake for the tablecloth trick is to pull out or to pull up and then down. And you don't want that ripple. I'm actually going to pull against this to whip it down. You're going to hear this whipping action almost as if you're going directly to your toes. So when you pull, the pull is not to you, it's down to your toes. And if you do it right, it looks like this. See, it's a direct down pull and you're left with it.
For example, a person in a car is moving at the speed of the car. If the car hits a tree, it will stop because of the force exerted by the tree. Because of inertia, the person will continue to move at the speed of the car until some force changes its motion. The seat belt, the dash, the windshield. Grim thought, huh? So there's an experiment with some blocks that you can do if you choose to. Or no, not that if you choose to, but what you think will happen. So remember, when you write a hypothesis, it's not meant for you to be 100% right. It is an educated guess of what you think would happen. You all are fifth graders. I know you're super smart. Don't change your hypothesis if you discover you are wrong. It's okay to be wrong. I want you to take that guess, take that risk, and put down what you think would happen. There's going to be a part 2 to this video. This is the end of part 1.